Hello and welcome to the Conversation Weekly. I'm Dan Merino in San Francisco.
And I'm Nihan and Hadi in Toronto.
Regular listeners to the show may be wondering, hey, wait a minute, where's Gemma? Well, Gemma is out on maternity leave. We're all very happy for her. And though she planned to come say her goodbyes to everyone, she is unexpectedly unavailable. She does send her regards. Nahal is one of our colleagues from the Canadian edition of The Conversation, where she covers science and technology, and we are super thrilled to have her on board with us for the next 8 or so months. Nahal, hello and welcome.
Hi, Dan. I'm delighted to be here, and I'm really excited to hear what we have going on today.
All right, you have every reason to be excited, because this week we're going back to the James Webb Space Telescope, or JWST, and we are approaching the 1-year anniversary of the telescope's launch, and it has been sending some really cool data back to Earth for about 6 months now. And we did an episode on the telescope last December, just ahead of the launch, and in that episode, we explained how this new telescope works, what its scientific goals are, and if you want a little refresher, there's a link to that episode in the show notes. But basically, to sum it up, James Webb Space Telescope is really big, really cold, and really good at seeing extremely faint objects in the universe.
This is really exciting. As the Science and Tech editor at The Conversation Canada, I've been paying attention to this story leading up to the launch and following it ever since. Remember those incredible images that came out over the summer? One of the ones that stuck with me the most was the Pillars of Creation.
Yes, I absolutely love all the old Hubble images of the Pillars of Creation, and it was so cool to see how James Webb's images were like so much brighter and more full of detail and all that stuff. And that's because what James Webb was designed to do, which people may have heard this phrase, first light, and James Webb being called the first light telescope, and that's because it's been designed to look back into the earliest days of the universe. And James Webb has led to some really incredible discoveries that are filling in this part of the history of the universe and kind of, well, everything. So to set the scene of what was going on in the early days of the universe, I called up an astronomer.
My name is Jonathan Trump, no relation. I'm an associate professor at the University of Connecticut, Department of Physics. I'm an observational astronomer. I use telescopes in space and on the ground to study distant galaxies and the black holes that lie within them.
Jonathan is part of the Cosmic Evolution Early Release Science Survey, or SEERS, a group of scientists who are studying the early data from James Webb Space Telescope.
So our best model for the universe that we live in is that it started with a bang, a big bang, right? And the universe, started from an infinitesimally small point with an infinitely high density, and then it rapidly expanded outward, right? And the universe began completely dark. It was crazy hot, temperatures exceeding any kinds of energies or temperatures we can create, even in the most powerful particle accelerators. There were no atoms like we have today. And eventually the universe started to cool as it expanded. And we started to get the very first stars which started to light up the universe.
So I'm familiar with the idea that the universe is expanding. Is that something the James Webb Telescope allows us to see?
Yes, sort of. So, like Jonathan said, the universe is expanding, but it's hard to see the ether of the universe expanding itself. But we can see objects that are within the universe, stars, galaxies, moving away from Earth as the universe expands. And the farther something is away from Earth, the faster it's moving away from us. And this is getting at a really important concept in James Webb called redshift. Nahal, have you heard of this phrase, redshift, at all?
I have, but I couldn't give you a precise definition of it.
Okay, so redshift is essentially the stretching of light, the shifting of light into the redder spectrums. If you think of a rainbow, we've got red, orange, yellow, green, blue, indigo, violet, and as you work your way up that spectrum, the wavelength of light, the distance between the peaks, gets shorter. When light comes from an object that's moving away from you on Earth, it's stretching out the light the faster that object is moving away from us. And if you're stretching out the light, you're shifting the light down towards the redder end of the spectrum. So when people say something is redshifted, it's essentially a measure of how fast an object is moving away from Earth. So the longer the redshift, the older the light is, and the farther away the galaxy emitting that light is.
That makes sense, because the James Webb Telescope is designed to use infrared light. So what is it showing us, or what have we learned from the information it's been sending back.
There's so much that's been learned already. And yes, the pillars of creation and all these nebula are so cool, but the interesting earliest galaxies, which is really what James Webb was designed to see, are not those pretty pictures. Behind all those beautiful parts of the universe are these little red smudges that if you were looking at those images, you probably didn't pay much attention to. But it's actually these little smudges that are the most ancient of galaxies. To explain some of what we've learned about these galaxies from the earliest days of the universe, I called up Jeyhan Kartaltepe, an associate professor of astrophysics at the Rochester Institute of Technology in the US. She's on one of the teams that's been working on one of these first batches of data taken from just a very particular slice of the night sky.
So this is a field of the sky known as EGS, or the Extended Growth Strip. It's an area of the sky that we've already looked at with Hubble before, so we had some information about it. It's in the northern hemisphere of the sky, right near the handle of the Big Dipper. And we used two modes primarily. One is the near-infrared camera called NIRCam, and the other is the mid-infrared instrument called MIRI. And so you can use these both simultaneously and get data at the same time. We took 4 different sets of images. I would say it's about 20 hours in total that we've spent. So the way we find galaxies in the very early universe has to do with their color. So these galaxies are completely invisible to a telescope like Hubble. We don't see any light in the visible part of the spectrum because that's really the rest frame UV light. So instead, what would have been visible light is in the infrared. And so that gives them sort of a telltale signature. Sometimes people refer to this as a dropout technique. It's there at one wavelength, and then it's gone when you look at it at a bluer wavelength.
Oh, interesting.
So basically, you're measuring the redshift that helps you pinpoint, when the light left that galaxy because of that telltale signature or drop-off. So we're looking at things, redshifts 7, 8, 9, 10 plus higher, which corresponds to the universe as it was at a few 100 million years old.
Can you be more specific versus than a few hundred, or is that just kind of what we're looking at? Like we don't actually have a specified...
Well, there's a large period of time we're interested in, right? So we're interested in, I'm kind of making a joke, 7, 8, 9 plus, which is a joke because we're finding things at redshifts 12, 13 and higher, which we didn't think we would.
Okay.
So there's actually a huge range of redshifts that we're interested in, which corresponds to a range of time in the universe's history.
So what else have you guys learned from this kind of earlier James Webb data?
Yeah, so one of the things we've learned is that there are more of these galaxies than we expected to see, which is a fun surprise. So it gives us more to work with and it's very exciting, but it poses a little bit of a challenge, right? If you asked us a year ago when we were planning like how many of these galaxies we would have found, we could give you a range, but what we're actually finding is pretty high on that range, right? We're finding more than we thought would be there.
So Dan, scientists are finding out that there are more galaxies than they expected to find and that they're even farther away, thanks to the James Webb Space Telescope being able to see using infrared.
Yep. So as Jeyhan was talking about, we're seeing more of these earliest galaxies than expected.
What have they learned about these galaxies more than them just being there?
Well, they've just got this preliminary data, so they can't tell too much. But looking at the shape of these early galaxies, people like Jeyhan are starting to be able to tell what these formation processes are like and how far along in the development phase these galaxies are, which is telling us a lot of surprising things about the nature of the early universe.
So there are a few big questions that we're hoping to answer. One is, how did those very first galaxies in the universe form? How did they form their stars? When did this process happen? So that's setting the very, very early stages of the universe. And then the other big question is, what happened after that? How did those galaxies evolve? How did they grow? How did they form their stars and change over time to become more like the galaxies we see today?
I know that a lot of your work is focused on what shape and size a galaxy is, and you've been trying to understand a lot of the galaxy structure from these earliest galaxies. But before we get into that, it would be great if you could just explain the general archetypes of galaxy shape today, so we can put the findings from James Webb in context.
Most of the galaxies we observe nearby us fall into 2 basic groups. They are spiral galaxies like our own Milky Way, or the nearby Andromeda galaxy that people are familiar with, or they're what we call elliptical galaxies. So they're just more roundish or footballish in shape. Spiral galaxies, they're basically a disc-like structure. They're very flat if you were to view them edge on. They can have a lot of spiral arms. They could have no spiral arms. Sometimes you just see a disc without very obvious arms. So there's a pretty big range. They can also have a bar through their center. So we think our Milky Way galaxy has a bar through its center as well. So our Milky Way galaxy is about 30,000 light years across. And so that's today's galaxies, but of course in the past they would have been much smaller. But there's a huge range, right? There's galaxies that are tiny, like the dwarf Magellanic Clouds that orbit our Milky Way galaxy, right? They're really small. And there are just huge behemoths like the galaxies in the centers of big galaxy clusters. Our Milky Way galaxy is a fairly large galaxy, though.
And what specifically is a galaxy you're looking for? Is it just a little red blob? Is it a spiral galaxy? Kind of what are you looking for when you're looking for some of these earliest galaxies?
So really any galaxy that we could see at these time periods would be interesting, but they have to be bright enough that we could observe them. So it wouldn't be those very first tiny blobs because they would be so faint we'd never see them. They come a little bit later, right? So you've already had a couple of generations of stars. Probably they've gotten to be big enough, massive enough, have enough stars that they're now bright enough that JWST can see them.
How does morphology come into this? So explain where your work on galaxy structure comes in.
I'm really interested in how the shapes of galaxies have changed over time, right? We know our own Milky Way is a spiral galaxy, and we want to understand how galaxies like that came to be and how the ones we observe in the very distant universe are different. With Hubble, when we look at these really high redshift galaxies, you see barely a smudge, right? There's only a couple of pixels in an image. You can't say very much about its shape other than it's there. And what's exciting about JWST is that we have the increased resolution that we can start to say something meaningful about the structures of these galaxies. And so that's their shape, that's their size, right? Physically, how big they are. And that's something we haven't been able to do before. So that was really exciting for us.
And what are you finding? What are these things looking like, and how big across are they? What are you finding?
So we're kind of finding a mix of things, right? Some of these are really small and compact, so you can't say too much about their shape. They look fairly round. Some are more extended. There's an interesting object that we found that's actually a pair, right? There's two things next to each other, and so they might be interacting with each other. We might be seeing one of the oldest mergers in the universe. We don't know.
Have you found any super young spiral galaxies or anything like that?
Yeah, so we've looked at things at a range of redshifts, and so we definitely see things that have disk structure out to pretty high redshift. That's a bit harder to say for some of these really extreme things because they're so much smaller, right? So the further away they are, also the smaller they look. And so it becomes harder to resolve a lot of features. So it's likely that some of these systems have disks, but I think that still remains to be seen.
So what's the youngest galaxy that you can see pretty good evidence that is a disk-shaped galaxy?
We've been able to see signatures of disks around galaxies all the way out to about a redshift of 7 or so. And for the even higher redshift galaxies, I think it's still to be determined, what their precise shapes are.
And were you expecting to find disk galaxies at a redshift of 7, or was this kind of a surprise when you started processing these first images?
I would say yes and no. It's always the answer. It's always a little bit of both.
Yeah.
I think to some degree we expect there to be disks because disks form pretty naturally in the universe whenever you have something that's rotating. What we don't really know is how fast that happens. And so I think we were expecting to see some, but we've been seeing a lot of them, which has been a bit of a surprise. The other thing we expect is that we see things that are messy, right? So they might have a disk, but they don't look at all like today's disk, right? We have this nice, evenly shaped spiral arm with a very thin disk. These are much more turbulent, right? There's a lot more gas, there's a lot more going on, so they're clumpier and messier. So it makes that dividing line of is it a disk or is it not a disk kind of complicated.
So you've been looking at the structure of these earliest galaxies, right? These disks or these more ovalish kind of globular clusters. Are we starting to understand the process of formation, like what's happening through time?
Yeah, so we do learn a lot by looking at them. And then the next step, will be to have spectra and learn more about the actual motions. Because with spectra, we can say, well, what is the rotation like, right? Which also gives us information about if it's a disk or not. So by looking at the shapes and structures of these galaxies, we learn a lot about them, and the properties of the stars that are forming in them. It tells us more than just what the shape is. It tells us something about the physical conditions of that galaxy and what the motion is like in that galaxy. So for example, a spiral galaxy has a spiral shape, but it has that shape because of the rotation of that galaxy. And an elliptical galaxy doesn't rotate in the same way, right? The stars in an elliptical galaxy are kind of buzzing all over the place. I like to think of it as like a beehive, right? It's not all moving. It's like one single, thing rotating, but the stars are going all over the place. And so the motions of the stars in those two types of galaxies are very different from one another. And so we can assume like, oh, hey, we see a disk. It's probably rotating. But we can also get that information through spectroscopic observations. And so if we were to be able to obtain spectra for these galaxies, we can see what the actual motion is, because one part of the galaxy that would be rotating toward us would be blue shifted and the other part would be red shifted. And so you can use spectra to actually say a bit about the motions, which will give us sort of more concrete evidence that something is actually a disk, around a galaxy.
You came in with a question, like what was going on in the early universe with regards to galaxy formation? Do you feel like you're starting to get an answer?
I think we are starting to get an answer. And the fun thing is that answer is giving us more questions. So it's definitely not all solved.
Of course.
There's more to do. And I think that's part of what makes it really exciting.
And I guess there's like kind of two questions here, right? There's the question of mechanism, like how it happened. And then there's a second question of when. And it sounds like from speaking with you and speaking with some of the other scholars we've spoken with, it sounds like kind of across the board, things are happening earlier than people necessarily predicted or expected based on theories and models. Is that a fair statement?
I think that is a fair statement. But we are definitely seeing that these galaxies formed earlier than we expected. That's why we're able to see more of them. And we're seeing things that have disks at fairly early times.
So what does this mean? Like, I mean, for someone in this field like yourself, when all of a sudden you say, wow, we know that there's this much happening at this age of the universe, like, how does that make you feel? If I'm going to put on my kind of therapist hat for a second. No, but like, seriously, like this has got to be pretty shocking or interesting or exciting result. But like, what does this really mean for people like you and your colleagues?
I mean, I think it's interesting because it tells us there's something we don't quite understand yet. We thought we understood things pretty well, but there's something in there that's a little different than we expected. And there's a lot of possibilities. There could be less dust in these galaxies than we expected, so they're brighter than we might have thought. It could be that there's something about the properties of dark matter in the very early universe that means, material is clumping together more quickly than we expected. It could be there's something called the initial mass function, which is an estimate of, for a given group of stars that form, how many of them are going to be really massive and how many of them are going to be less massive. Well, maybe there's more, really massive stars forming than there are the little guys than we expected. And so that's changing, how rapidly these things were able to grow. So there's a lot of possible mechanisms which mean different things, but we don't yet know which of these will turn out to be the case.
And how do you go to test some of these theories? Like what was wrong with our models?
So there's a number of different ways to test these theories, and it always involves getting more data, of course.
Yeah, of course.
So right now we've just barely touched the tip of the iceberg with these surveys, and we've found, small numbers of things. But over time, we're going to be observing many, many more, and many really bright ones as we start to cover larger areas. And how many we see at different brightnesses tell us something about the mechanisms, because you can make predictions for how many really bright things versus how many faint things, but you need a lot of objects to have those statistics. We'll get there. We're not quite there yet. The other thing is spectroscopy, right? Spectroscopy is kind of like the holy grail for astrophysics, for really being able to nail down the physics. At the moment, all of these sources are candidates at these redshifts, right? We have an estimate of their redshift because of those colors, like I mentioned, but we really need spectra of them to say definitively that they are the distance we think they are. So some of them might drop out, which will change our picture a little bit. Some of them will be bona fide, at these redshifts.
So with the data that's being sent back from the James Webb Space Telescope, what we're learning is that there's so much more for us to discover.
Ain't that the truth of science? There's always more to learn the more we know. But in addition to these galaxies existed very early on in the universe and a little bit about their structure, James Webb is just starting to give us clues about the actual chemical composition of these earliest galaxies.
And what is the actual early composition of these galaxies?
Well, Jonathan Trump, who we heard from earlier, is actually studying this very question of the chemical composition of the early universe, so I'll let him explain what was going on just after the universe began.
When the Big Bang happens, it's really just hydrogen and helium. Trace heavier elements like lithium, but almost entirely 75% hydrogen, 25% helium. Everything else, all the other elements in the universe, these more enriched chemicals that make up the periodic table, came later.
So how do we go from the most basic building blocks up to a full star and the heavier elements?
Yeah, so as the universe expanded, it started to cool, and we now have these atoms, this hydrogen and helium, able to start collecting and collapsing in on itself because it's now cold enough that it can start to collapse under its own gravity. These just collections of hydrogen and helium, eventually it becomes dense enough that in its center it is tremendously dense, it is tremendously hot, tens of millions of Kelvin, which is still tens of millions of degrees Celsius, and it can start undergoing thermonuclear fusion, right? So the temperatures and densities are so hot that we can actually overcome the electromagnetic repulsion of, two positively charged atoms, two hydrogen atoms, smash them together and start to make heavy elements, right? And in the center of our sun, this is ongoing now. It's why our sun is so bright, despite us being so far away. We begin by smashing hydrogen into another hydrogen. Do this 2 more times, we get a helium atom, right? With 2 protons, 2 neutrons. Then we smash actually 3 helium atoms together. We get carbon, right? Then we smash another helium atom on top of that. We get oxygen. Right. And so carbon and oxygen in particular, we know are incredibly important for the development of life, right? Oxygen, one of the key atoms in water, for example, in the air we breathe, carbon dioxide in the, what we breathe out. Of course, we know that carbon is a fundamental building block of all life. My colleagues and I were particularly interested in how do you build this periodic table, right? And how quickly do the first stars in the first galaxies have fusion to assemble the rest of the periodic table, successive generations of fusion, hydrogen becoming helium, helium becoming carbon, oxygen all the way up. Fusion happens in the center of a star. To get those elements out of a star, right, that star has to expel them somehow. And this typically happens in massive supernovae, right, stellar explosions. And so how quickly do those stars evolve and really die and explode as supernovae so that they can spread those heavy elements onto other stars and onto the stuff that forms disks around stars that eventually collapses down into planets. So really 2 questions, right? How quickly do stars make the elements? And how quickly do they spread those elements for successive generations of star and planet formation?
And so what were you looking at with James Webb, and how were you able to tell what elements are present in a dust cloud, galaxy formation, whatever, from, a couple 100 million years post-Big Bang?
That's right. Yeah, it's just a few 100 million years after the Big Bang. We used spectra, mid-infrared spectra from JWST.
So how does that work?
Yeah, it's very similar to a fluorescent light, like I have here in my office. Fluorescent light bulbs work because you have electrons bouncing around in atoms, right? Perhaps neon in a fluorescent light bulb. And those electrons, actually, we also observe neon in these distant galaxies. So it's even better of an analogy than I was thinking at first. We see electrons bouncing from higher energies to lower energies. When they do that, they put off very particular energy photons, very particular energy particles of light. And you end up with very discrete emission lines in a spectrum, right? A spectrum just being the dispersed light, like a rainbow. But unlike a rainbow that we get from our sun, for example, which is nice and smooth, a rainbow from a fluorescent light bulb ends up being narrow spikes, right? At very particular colors. This is quantum mechanics, and the energy in an atom is quantized, has a very particular energy. And so we look at these distant galaxies and we look for particular patterns of emission lines. We often call them chemical fingerprints, right? So it really is like a particular fingerprint of particular elements in the gas in a galaxy, just like a fluorescent light bulb. And some of those elements we identify are neon, just like we have in fluorescent light bulbs. But we also in particular look for oxygen, carbon, some of these other heavier elements beyond just hydrogen and helium.
So if I can just kind of try and sum this up, it's almost like if you held up a prism to our sun, right? We get a nice smooth rainbow. But if you hold up a prism to, say, one of these early galaxies, there's going to be brighter spots at certain colors, missing certain colors. And all of this pertains to the actual chemical composition of the stars or the galaxy or whatever.
Yeah, that's absolutely right. That's absolutely right. Yeah, we use a grating, not a prism, but otherwise, yeah, it's exactly right.
So what have you seen with JWST?
So my study particularly focused on 5 galaxies, all at redshift greater than 5, which is about within the first billion years of cosmic time. The highest redshift of these is something like redshift 8.5, which is, I think, about 400 million years after the Big Bang, up to about a billion years after the Big Bang. 5 galaxies in a field of view of the sky, which is roughly 2 by 2 arc minutes. An arc minute is about the same size if you hold your finger at arm's length and look at the thickness of your thumbnail, right? Not the width of your thumbnail, but the thickness of your thumbnail. That is 1 arc minute. Put 2 of those together, that's 2 by 2 arc minutes. We had 5 galaxies.
So we're talking tiniest little sliver here, right?
That's right. That's right. We call this a tiny pencil beam survey, although it's more like the tip of a pencil, held out on the sky. Just a tiny area of the sky, 5 galaxies, all within the first billion years of cosmic time.
Jonathan's team actually got their data right around the same time as Jeyhan's. And this data is from that first press conference held at the White House that celebrated the first images from JWST.
This is part of the SMACS galaxy cluster. I think people call it something like Webb's first deep field. It's the image that was released to much fanfare in that first White House press release, right? And there's a bunch of, tiny itty bitty red smudges in the background behind these beautiful arcs, and spirals and massive elliptical galaxies. Behind that, these tiny itty bitty red smudges, that's what I was most interested in because those are some of the first galaxies in the universe.
What did you find?
Yeah, so there were some lines that were particularly strong, right? Some lines of oxygen, a line of neon that seemed to be particularly strong, stronger than we typically observe in low redshift galaxies. In some sense, this is immediately surprising because if these galaxies were not very enriched, we might have guessed that we wouldn't see these heavier chemical elements, right? Sure. We would have guessed that the only strong lines might be hydrogen and helium. So immediately we saw, these things have to be relatively enriched. We also found that higher energy emission lines which correspond to more ionized atoms that have lost more electrons, those lines were stronger.
Does that mean just there's a larger volume of oxygen, for example, or the oxygen is somehow shining brighter? What do you mean by that?
So we found that lines that correspond to oxygen that has lost a whole bunch of electrons, right? Those lines were very strong compared to oxygen that had not lost many electrons.
Oh, so even within the oxygen color, there's subcolors of oxygen based on how many electrons have been stripped off. Exactly. And so we could actually measure the ionization state of the gas, how much that gas had been ionized. And so, using that ionization state, we found the gas is pretty extreme, right? It's highly energetic. It's ionized a lot. It's probably also high density, high pressure. Not like gas in galaxies in the Milky Way, for example, which is a lot more calm. There was a surprising amount of enrichment. I would have guessed that we would have found a not very enriched universe, that the universe would, have struggled to make the periodic table, to build up things heavier than hydrogen and helium. That's not what we found. Instead, the universe seems to have proceeded pretty rapidly. So what is the significance of that here?
We don't entirely know, but it hints at a bunch of possibilities, right? So the gas in these galaxies was also highly energetic, more energetic than the gas we observe in galaxies in the teenage universe and in the universe today. And this might point to more accretion onto supermassive black holes in the galaxy centers.
Explain what you mean by that. More accretion. Does the bigger black holes are sucking in more denser gas? What do you mean?
More matter falling onto black holes. Okay. So as matter falls into black holes, of course, once the matter gets too close, it falls within the event horizon. We never see it. But beyond the event horizon, this matter will usually fall into an accretion disk. That disk is very close to a massive object. It has to orbit that massive object very rapidly. And it is highly energetic, more energetic than we usually get when it comes to like starlight, for example. And so we know that matter falling onto supermassive black holes can be very, very energetic in its light emission. So it can end up ionizing gas. It can end up making that gas very, very energetic. So that's explanation possibility number one, right? Another possibility is that the stars that form in these galaxies may be more massive and, because they're more massive, more energetic than the stars that form in galaxies like the Milky Way today, right? There might be paths for stars to become more massive because they start off only made up of hydrogen and helium. And those very, very massive early stars are likely to be very, very energetic and may also provide a path to making the gas in these galaxies so ionized, so energetic. So, we don't have a firm grasp yet of what's causing this ionization, but certainly it points to something that is quite a bit more extreme than we normally see in galaxies today. And so this was really just a first look, 5 galaxies, a field of view, that is just 2 by 2 arc minutes, a tiny, tiny tip of a pencil survey of the sky. And so I'm really, really excited to think about what we're going to keep learning, right? As we do more and more of these programs and we actually get to make a proper survey, of a larger field of view of the sky. And as we get a better feel for the diversity of galaxies within the first billion years, instead of going beyond 5 to 50 to 500.
Even though this first study was done on just 5 galaxies, collected over a short period of time, I wondered, was there anything that Jonathan and his colleagues had seen in that data that they hadn't expected?
The biggest surprise to me was that these galaxies are surprisingly enriched. I would not have guessed that. I would have expected, that the most prominent elements we'd see in their spectra would be hydrogen and helium, right? But instead, we had these big booming oxygen lines. We had a surprising neon line. That was what surprised me the most. I think, it was not as big a surprise that the galaxies were so extreme in terms of their energetic properties. And we know the universe in many ways was simply more extreme in those first billion years. The whole universe was smaller and hotter, until today it expands and cools. But the fact that they were already so enriched was a big surprise to me. I would not have guessed that. And I think most theorists would similarly not have guessed that.
And why? Is it because you would have expected this to be somewhat linear in the production of elements or something? Like, where did that discrepancy come from?
Yeah, it points to either stars are more efficient at somehow fusing elements, perhaps because they're more massive in the early universe, or perhaps they're more efficient at spreading those elements out. Maybe the pace of fusion is not really that different, but the stars explode quicker or spread their heavier elements, more massive chemicals around more quickly than they do in galaxies today. So one of those things must be true based on the observations, and neither of those things were necessarily predicted in our best ideas for the theory of the early universe.
So what do you expect to learn as you get more data from JWST and expand the sample of galaxies you're looking at?
I think we're going to be able to understand better, did we just happen to get a weird sample in this very first look of these galaxies that are enriched, or are most galaxies like this? We'll also start to find more oddballs, right? We'll start to find things that perhaps are really primordial and really only have signatures of hydrogen and helium. I also think we'll find oddballs like some of the very first supermassive black holes forming in these galaxies. This has been a long time interest of mine, of my research program. We now know that every galaxy has a supermassive black hole in the center. Our Milky Way galaxy has one. It's in Sagittarius. We call it Sagittarius A star. Right out of the spout of the teapot, that's what Sagittarius looks like to me. Every galaxy has one of these, but we don't know if galaxies start with black holes or if those supermassive black holes come later. I think of it like a chicken or egg problem.
Oh, interesting.
Yeah. And so I want to tackle this chicken or egg problem. Do these galaxies in the early universe have black holes in the beginning, when they're little babies? Or do the black holes develop later from matter falling to the center of the galaxy, eventually making a very, very dense singularity?
All right, so while we're all oohing and eyeing over these images from the James Webb Space Telescope, Jonathan and his colleagues are scouring these images to learn what our universe is made of.
Yes, pretty much every astronomer on Earth is excited about the kinds of questions that could be answered with the James Webb Space Telescope. Just like Jonathan, right? Talking about black holes, chemical compositions of galaxies, and also of distant exoplanets that might have to do with the search for life. There's just so much we can do. And one thing that we heard from every person we spoke to for this episode is that James Webb really could do a lot of this work because the images it is collecting are incredibly high quality, even better than people were expecting. The level of detail is just phenomenal.
It sounds like the scientists are really optimistic that they'll find much more as time goes on and the James Webb Space Telescope collects and sends back more data.
Absolutely. And time is really this key part of the puzzle here because these first results that a ton of science has already come from were really just done using quick surveys of the sky, not looking at anything in particular for very long, and it's already blowing all previous telescopes out of the water. And in the coming months and years, James Webb is going to start doing follow-up surveys of some of the more interesting things that astronomers have seen.
And what do these follow-ups entail?
So a follow-up survey basically just means picking something in particular and pointing the telescope at it for much longer, right? We have a couple hours or a couple days even on some of this early stuff. We're talking like many days or even weeks of observation time. And the longer you do this, the better the images you get, unsurprisingly. And in fact, there's a formula that you can use to calculate the relationship between image quality and observation time. I'm going to let Michael Brown explain that. He is a professor of astronomy at Monash University in Australia and has been working with some of this early James Webb data.
A typical observation might be hours of exposure time, or perhaps in some cases a day or two. But for some of these deep fields, it's weeks of observing time. And there is a bit of diminishing returns in the sense that signal to noise, which is how we apply the quality of the observations, goes as a square root of the amount of time, which basically means if you want to double the quality of the observations or the depth, we have to observe for 4 times the amount of time. And so the time with it's been precious. And so, I've been on science papers that have used, literally a couple of minutes of data.
Really? Just a couple minutes?
It's just a couple of minutes. And it's like,
wow,
these galaxies are relatively bright. It doesn't take long to get the image per se, but the extra resolution, the extra image quality is just so good that a couple of minutes can do amazing things. So yeah, the initial time's really precious. It's like, quick, let's get as much as we can, on the off chance that it suddenly breaks,
Sure. Yeah.
There is that little terrible voice at the back of your head that goes, let's quickly get all the things.
It's understandable that Michael and I imagine a lot of other astronomers were extremely worried in those first few days after JWST started collecting data, but Michael is now very optimistic about the future that is in store for JWST.
One thing I keep thinking of is we were in the early days. It's like Hubble in the early 90s. And a lot of the surprising stuff with Hubble came later as we sort of realized what it could do and what we were actually seeing. So I'm enjoying our level of ignorance right now and where we're going to be going in the next 5 to 10 years. I'm very comfortable with that given the history of science. So it's just fun seeing this and going, I don't know how I'd start to interpret this just now. And it's just this huge level of complexity. I think one of the things that I want to convey about James Webb in the early days is it's good fun. And while I'm a galaxy person, one of the things that I've just enjoyed about James Webb is all the other different aspects of astronomy. So things such as the atmospheres of planets orbiting other stars, or the image of Jupiter where you can see the aurora and the rings, and you get to connect with the sense of wonder. There is a risk when there's a new telescope and you're a professional astronomer that's like, my God, it's full of work. But you can get genuinely excited, not just about the data and the images and the spectra in your own field, but across all of astronomy as, these really exciting results come through. And, it's a great reminder of the sense of fun that you can have in science and see all this new data coming through. And it's just nice to have that in one's professional and broader life.
That's it for this week's episode. Thanks so much to Jonathan Trump, Jeyhan Kartaltepe, and Michael Brown for speaking with us. This is our final full episode of 2022, but we do have one more Discovery episode coming your way, but we will be returning with new episodes starting in January. You can find us on Twitter at TC_audio, on Instagram at theconversation.com, or email us podcast@theconversation.com. If you like what we do, please support the podcast and the conversation more broadly by going to donate.theconversation.com.
This episode of The Conversation Weekly was produced by Mariwany and Katie Flood. It was written by Katie Flood and Dan Merino. Sound design was by Eloise Stevens, and our theme music is by Neeta Sarl. Mariwany is our interim executive producer, and Stephen Kahn is our global executive editor. Alice Mason runs our social media, and Soraya Nandi does our transcripts. I'm Nihal El-Hadi.
And I'm Dan Marino. Thank you all for listening, and see you next year.